I'm here. I made it. Are y'all ready to learn? I'm ready to learn ya. Maddie's ready. No, she's not. She's asleep. No. Alright. We're gonna get typing. I'm trying to cover the keyboard again because that helped actually quite a bit. Okay. Sure, I'm clicked over here. How y'all doing? It's been a while. Oh my goodness. That is so loud, but I think in a good way. Excuse me. Thank you, Michael. Got the prime.
Maddie, wake up.
No, oh, look at her. She needs her resting. There, I'll be like that so you can see her better. All right. Moving the keyboard so it's fully blocked. Okay. Are we ready? I don't feel ready. All right. I had to just figure out where my first fingers go. Let's go. Ah! Already off to a bad start, but we're rusty. It's been a while. Trying to squeeze in a stream. Things have been hectic and I'm gonna be traveling soon, so it's gonna still be hectic, but I want to keep up with these streams. I don't want to. I'm looking now. Hang on. Ooh. Can you use your headphones that I've left you? Please. K, where's K? Middle finger? Yes. Oh no. Where? Uh-oh. We're gonna have to look. What the hell? I feel like I was hitting there like a good... Okay. I don't know. Don't ask me. I was not having it? What? Oh, no. Wait. No space? Oh, or shift, I mean. Goodness gracious. Engine. The I wasn't. I was like, what weren't you having? What's up? Maddie, why right now? Everybody's in the middle of a test. I feel like I want to start over, but I don't want to drag this out longer than it needs to be. I'm just gonna look in. It's when it's the symbols I struggle. But that's the whole point of doing these tests instead of just like regular writing, like English ones. Q. All right. Oh. Sometimes this keyboard's like really sensitive. It'll register like a double tap. So I feel like that's not my fault, but I do need to take that into consideration, that that's my keyboard, you know? Oh, fuck. Okay. Ooh. See, sometimes my brain just takes a second to breathe, and then it's like, bloop, 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 bloop. I know where everything is. And I'm like, well, can't you do that all the time? So I just need to figure out how to register or like get into that range, you know? And get into that flow state, I guess. Like certain words, my brain is like, yeah, I can write that easy. Come on! Okay. Q. Shit. Nope. Oh, I took a risk. That was like a leap of faith. Okay. Oh no. Oh. I got scared. Where's G? I don't know. I keep looking. I is gonna get me though. Shit. No. Ugh, and my misery. No. I hit control. Literally me right now. No. 12. I think 18 was last time, and I was upset with that. That one was bad. That was bad. We'll see how we are at the end. All right. I've been really, really looking forward to this. My keyboard gets to be over here now. I get to look. I don't care. I've got a cafe mocha. All the ice is melted, so it's okay now. 2.13. How to design your first programs. Now that you've learned some basics about programs, let's look more closely at how to design a program. When you sit down to write a program, generally you have some kind of idea which you'd like to write a program for. New programmers often have trouble figuring out how to convert that idea into actual code. But it turns out you have many of the problem-solving skills you need already acquired from everyday life. The most important thing to remember and the hardest thing to do is to design your program before you start coding. In many regards, programming is like architecture. What would happen if you tried to build a house without following an architectural plan? Odds are, unless you were very talented, you'd end up with a house that had a lot of problems. Walls that weren't straight, a leaky roof, etc. Similarly, if you try to program before you have a good game plan, moving forward, you'll likely find that your code has a lot of problems. You'll have to spend a lot of time fixing problems that could have been avoided altogether with a little thinking ahead. A little upfront planning will save you both time and frustration in the long run. In this lesson, we'll lay out a generalized approach for converting ideas into simple functional programs. Is there an ad here? Ooh. Fun. Design step 1. Define your goal. In order to write a successful program, you first need to define what your goal is. Ideally, you should be able to state this. I'm having an issue because I'm using the noise canceling. Maybe that's better. Or like I had the noise canceling off, so it's like noise room just sounded weird. I don't know. This is better. I feel better. In order to write a successful program, you first need to define what your goal is. Ideally, you should be able to state this in a sentence or two. It is often useful to express this as a user-facing outcome. For example, allow the user to organize a list of names and associated phone numbers. Generate randomized dungeons that will produce interesting-looking caverns. Generate a list of stock recommendations for stocks that have high dividends. Model how long it takes for a ball dropped off a tower to hit the ground. Although this step seems obvious, it's also highly important. The worst thing you can do is write a program that doesn't actually do what you or your boss wanted. Ooh, I ain't got no boss. I am my own boss. Design step 2, define requirements. While defining your problem helps you determine what outcome you want, it's still vague. The next step is to think about requirements. Requirements is a fancy word for both the constraints that your solution needs to abide by, like budget, timeline, space, memory, etc., as well as capabilities that the program must exhibit in order to meet the user's needs. Note that your requirements should similarly be focused on the what, not the how. For example, phone numbers should be saved so they can be recalled later. The randomized dungeon should always contain a way to get from the entrance to an exit. Stock recommendations should leverage historical pricing data. The user should be able to enter the height of the tower. We need a testable version within 7 days. The program should produce results within 10 seconds of the user submitting the request. The program should crash in less than 0.1% of user sessions. A single problem may yield many requirements, and the solution isn't done until it satisfies all of them. Okay. Design step 3. Define your tools, targets, and backup plan. When you are an experienced programmer, there are many other steps that typically would take place at this point, including defining what target architecture or OS your program will run on, determining what set of tools you'll be using, determining whether you will write your program alone or as part of a team, defining your testing, feedback, release strategy, determining how you will back up your code. Ooh. However, as a new programmer, the answer to these questions are typically simple. You're writing a program for your own use, alone, on your system, using an IDE you downloaded. Your code is probably not used by anybody but you. This makes things easy. Excellent. We got dishwashers. Campos America. That said, if you are going to work on anything of non-trivial complexity, you should have a plan to back up your code. It's not enough to zip or copy your source directory to another location on the same storage device. If your storage device dies or becomes corrupted, you'll lose everything. Copying or zipping to a removable storage, a flash drive, is better, though you still risk losing everything in the event of theft, fire, or significant natural disaster. The best backup strategy involves getting a copy of your code onto a machine that exists in a different physical location. There are lots of easy ways to do this. Zip it up and email it to yourself. Oh, that is smart. Upload it to a cloud storage service like Dropbox. Oh. Mm-hmm. Use a file transfer protocol, SFTP, to upload it to a server you control, or use a version control system residing on another machine or in the cloud. Version control systems have the added advantage of not only being able to restore your files, but also to roll them back to a previous version. Ooh. Like, we just bombed this, like, let's recover what we had. Design step 4, break hard problems down into easy problems. In real life, we often need to perform tasks that are very complex. Trying to figure out how to do these tasks can be very challenging. In such cases, we often make use of the top-down method of problem solving. That is, instead of solving a single complex task, we break that task into multiple subtasks, each of which is individually easier to solve if those subtasks are still too difficult to solve, they can be broken down further. By continuously splitting complex tasks into simpler ones, you can eventually get to a point where each individual task is manageable, if not trivial. Let's take a look at an example of this. Let's say we want to clean our house. Our task hierarchy currently looks like this. Oh my god, there's so many ads right now. Clean the house. We need to clean the house. So what do we need to do for clean the house? Cleaning the entire house is a pretty big task to do in one sitting, so let's break it into subtasks. Clean the house means vacuum the carpets, clean the bathrooms, clean the kitchen. That's more manageable as now we have subtasks that we can focus on individually. However, we can break some of these down even further. Like we need to vacuum the carpets, but we also need to scrub the toilet and wash the sink in the bathroom. Yuck. Clean the kitchen, we need to also clear the countertops, clean the countertops, scrub the sink, take out the trash. Okay. Now we have a hierarchy of tasks. None of them particularly hard. By completing each of these relatively manageable sub-items, we can complete the more difficult overall task of cleaning the house. The other way to create a hierarchy of tasks is to do so from the bottom up. In this method, we'll start from a list of easy tasks and construct the hierarchy by grouping them. As an example, many people have to go to work or school on weekdays, so let's say we want to solve the problem of go to work. If you are asked what tasks you did in the morning to get from bed to work, you might come up with the following list. Oh, just keep it tiny from the beginning. Pick out clothes, get dressed, eat breakfast, travel to work, brush your teeth, get out of bed, prepare breakfast, get on your bicycle, take a shower. Using the bottom-up method, we can organize these into a hierarchy of items by looking for ways to group items with similar. We can organize these into a hierarchy of items by looking for ways to group items with similarities together. I'm getting tripped up. So this is all over the place. Like it's not ordered at all. So we can just use this unordered list and then organize it in the hierarchy. Oh. Group all the ones that that's a fun way to do it, actually. Like coding things or art things or sound things, Get from bed to work. Bedroom things. Turn off alarm. Get out of bed. Pick out clothes. Bathroom things. Take a shower. Get dressed. Brush your teeth. Breakfast things. Make coffee or tea. Eat cereal. Transportation things. Get on your bicycle. Travel to work. As it turns out, these task hierarchies are extremely useful in programming, because once you have a task hierarchy, you've essentially defined the structure of your overall program. The top level task, in this case clean the house or go to work, becomes main, because it is the main problem you're trying to solve. The sub-items become functions in the program. Okay. If it turns out that one of the items, functions, is too difficult to implement, simply split that item into multiple sub-items, sub-functions. Eventually, you should reach a point where each sub-function in your program is trivial to implement. Okay. Design step 5. Figure out the sequence of events. Now that your program has a structure, it is time to determine how to link all the tasks together. First step is to determine the sequence of events that will be performed. For example, when you get up in the morning, what order do you do the above tasks? It might look like this. Bedroom things, bathroom things, breakfast things, transportation things. If we're writing a calculator, we might do things in this order. Get first number from user, get mathematical operation from user, get second number from user, calculate result, print result. At this point, we're ready for implementation. Ooh. Implementation. Step 1, outlining your main function. Oh, okay. Now we're ready to start implementation. The above sequences can be used to outline your main program. Don't worry about inputs and outputs for the time being. Okay, so you're like, I want these to be the functions, so let me just put a note here before I start. Or in the case of the calculator, get first number from user. Get mathematical operation from user, get second number, calculate result, print result. Note that if you're going to use this outline method for constructing your programs, your functions won't compile because the definitions don't exist yet. Commenting out the function calls until you're ready to implement the function definitions is one way to address this, and the way we'll show here. Alternatively, you can stub out your functions, create placeholder functions with empty bodies, so your program will compile. That's like a forward declaration, right? Function declaration? I don't know. Implementation. Step 2. Implement each function. In this step, for each function, you'll do 3 things. Define the function prototype, inputs and outputs. Write the function, test the function. If your functions are granular enough, each function should be fairly simple and straightforward. If a given function still seems overly complex to implement, perhaps it needs to be broken down into subfunctions that can be more easily implemented. Or it's possible you did something in the wrong order and need to revisit your sequencing of events. Let's do the first function from the calculator example. All right, include the IO stream. Function is get user input. So we're going to character output, enter an integer. And then input, we're initializing character input to input, and then return what input is. That is the function. Now we have main. So main runs first. Get input runs this. Character output. All right, get first number from user. Note we've included code here to test the return value. Debug code to ensure get user input is working. We'll remove this later. Interesting. Get mathematical. Okay, so we started. So it's like this is another function we need to do. This is just the first one that we put down. First, we determine that the getUserInput function takes no arguments and will return an int value back to the caller. That gets reflected in the function prototype having a return value of int and no parameters. Next, we've written the body of the function, which is a straightforward 4 statements. Finally, we've implemented some temporary code in function main to test that function, getUserInput, including its return value. Finally, we've implemented some temporary code in function main to test that function getUserInput, including its return value, is working correctly. I got tripped up in the parentheses. We can run this program many times with different input values and make sure that the program is behaving as we expect at this point. If we find something that doesn't work, we know the program is in the code we've just written. Once we're convinced the program is working as intended up to this point, we can remove the temporary testing code and proceed to implementation of the next function. Function get mathematical operation. We won't finish the program in this lesson as we need to cover some additional topics first. Oh, I didn't realize that. Remember, don't implement your entire program in one go. Work on it in steps, testing each step along the way before proceeding. Because if you write the whole thing, you're like, no, I know. And then it doesn't work, then you have to go through everything. Don't want to do that. We cover testing in more detail in lesson 9.1, Introduction to Testing Your Code. Implementation, step 3, final testing. Once your program is finished, The last step is to test the whole program and ensure it works as intended. If it doesn't work, fix it. Words of advice when writing programs. Keep your program simple to start. Often new programmers have a grand vision for all the things they want their program to do. I want to write a role-playing game with graphics and sound and random monsters and dungeons with a town you can visit and sell the items that you find in the dungeon. If you try to write something too complex to start, you will become overwhelmed and discouraged at your lack of progress. Instead, make your first goal as simple as possible, something that is definitely within your reach. For example, I want to be able to display a two-dimensional field on the screen. Okay. Add features over time. Once you have your simple program working and working well, then you can add features to it. For example, once you can display your field, add a character who can walk around. Once you can walk around, add walls that can impede your progress. Once you have walls, build a simple town out of them. Once you have a town, add merchants. By adding each feature incrementally, your program will get progressively more complex without overwhelming you in the process. Focus on one area at a time. Don't try to code everything at once, and don't divide your attention across multiple tasks. Focus on one task at a time. It is much better to have one working task and 5 that haven't been started yet than 6 partially working tasks. If you split your attention, you are more likely to make mistakes and forget important details. Test each piece of code as you go. I'm parched. Hang on. Gosh, it like settles at the bottom and then it's like kind of chalky. Like mocha powder. Okay. Test each piece of code as you go. I'm trying to make sure I read that the first one. Test each piece of code as you go. New programmers will often write the entire program in one pass. Then, when they compile it for the first time, the compiler reports hundreds of errors. This can not only be intimidating if your code doesn't work, it may be hard to figure out why. Instead, write a piece of code, then compile it, and test it immediately. If it doesn't work, you'll know exactly where the problem is, and it will be easy to fix. Once you are sure that code works, move to the next piece and repeat. It may take longer to finish writing your code, but when you're done, the whole thing should work, and you won't have to spend twice as long trying to figure out why it doesn't. I love that. Don't invest in perfecting code early. The first draft of a feature or program is rarely good. Furthermore, programs tend to evolve over time as you add capabilities and find better ways to structure things. If you invest too early in polishing your code, adding lots of documentation, full compliance with best practices, making optimizations, you risk losing all of that investment when a code change is necessary. Instead, get your features minimally working and then move on. As you gain confidence in your solutions, apply successive layers of polish. Don't aim for perfect. Non-trivial programs are never perfect, and there's always something more that could be done to improve them. Get to good enough and move on. Okay, I'll try. Optimize for maintainability, not performance. There is a famous quote by Donald Knuth that says, premature optimization is the root of all evil. Okay. New programmers often spend far too much time thinking about how to micro-optimize their code, trying to figure out which of the two statements is faster. This rarely matters. Most performance benefits come from good program structure, using the right tools and capabilities for the program at hand, and following best practices. Additional time should be used to improve the maintainability of your code. Find redundancy and remove it. Split up long functions into shorter ones. Replace awkward or hard to use code with something better. The end result will be code that is easier to improve and optimize later, after you've determined where optimization is actually needed, and fewer bugs. We offer some additional suggestions in lesson 3.10, finding issues before they become problems. Hydrate. I don't have any water. I had a professor that used to tell me the same thing. It's good enough. Drive me mad. Yeah. I'm like, it's not perfect. It's trauma. Complex system that works is invariably found to have evolved from a simple system that worked. John Gall. Semantics. How systems really work and how they fail. Okay. Conclusion. Okay, here we are. I'm gonna have to take a break so I can get some water. I might have a peanut butter sandwich too, actually. Like now. Conclusion. Many new programmers shortcut the design process because it seems like a lot of work and or it's not as much fun as writing the code. No, that all looked fun, honestly. However, for any non-trivial project, following these steps will save you a lot of time in the long run. A little planning up front saves a lot of debugging at the end. Key insight. Spending a little time up front thinking about how to structure your program will lead to better code and less time spent finding and fixing errors. Reader Emeka Daniel comment on this website. I would say this is arguably the most important thing in programming, and some of us, like me at first, took it for granted. Ooh. As you become more comfortable with these concepts and tips, they will start coming more naturally to you. Eventually, you'll get to the point where you can write entire functions and short programs with minimal pre-planning. Okay. Let's see how short this is. Alright, it is Quiz City. And I do need to check out my ad blocker. She's being a little silly. I mean, maybe I don't know. It's freaking me out. Oh my god. Oh, it's everywhere. Alright, I'm gonna BRB. Be right back. I'm back. I have water. I ate something. I fixed the ad blocker. Maddie's here. May not seem like it. Oh my gosh. Ooh. You just blend right in. Okay. Oh, she looks so cute. All right. Get all the water. Also, I have this. I think I'm ready for it. I went to Ace Hardware store. Okay. Don't judge me. Please don't judge me. It was an impulse. I grabbed it and then I kind of was like, it's a little bit open. I don't really want it. And then the cashier was like, "Are you getting this?" And I was like, "Oh, no, actually I changed my mind." And he was like, "Okay." And then he was like scanning it and he like kept trying to scan it. So I felt really bad. So I was like, okay. It was 29 cents. And then I was like, I'll probably just throw it away. But now it's caramel apple. It's like an apple lollipop, but with caramel around it. I think it's worth it. I trust Ace Hardware. I think. Okay, that's what we're working with. Is it worth it? Is there anything out of the norm? I may be being overly cautious, but taking a risk here, All right, I'm gonna do it. We're going in. It's nice. I think we're good. Let's hope. I've been watching too much House. That's what the problem is. Okay. I'm like, Listeria. No, it's like, what? Safety's important. Yes. All right. We have water to hydrate. Yeah, that's what's going on. All right. 2.x. Chapter 2, Summary and Quiz. Chapter Review. A function is a reusable sequence of statements designed to do a particular job. Functions you write yourself are called user-defined functions. A function call is an expression that tells the CPU to execute a function. The function initiating the function call is the caller. Excuse me. I had peanut butter sandwiches. They're getting down there. And the function being called is the callee, or called function. Do not forget to include parentheses when making a function call. The curly braces and statements in a function definition are called the function body. A function that returns a value is called a value returning function. The return type of a function indicates the type of value that the function will return. The return statement determines the specific return value that is returned to the caller. That's too many returns. A return value is copied from the function back to the caller. This process is called return by value. Failure to return a value from a non-void function will result in undefined behavior. The return value... Oh, the song, sorry. The guitar got me. I need some lollipop time. I don't know what the name of this one is. 1988 is the name of the song. Excuse me. Okay. I lost my place. Oh. The return value from function main is called a status code. It tells the operating system and any other programs that called yours, whether your program executed successfully or not. What? Why am I reading it like that? The return value from function main is called a status code, and it tells the operating system and any other programs that called yours, whether your program executed successfully or not. Okay. The parentheses constantly are tripping me up, and he uses them so much, or she. By consensus, a return value of 0 means success, and non-zero return means failure. Practice dry programming. Don't repeat yourself. Make use of variables and functions to remove redundant code. So we don't have to continuously ask the user for an input. We just have an input function, and we call it anytime we need it. Functions with a return type of void do not return a value to the caller. Function that does not return a value is called a void function or non-value returning function. Void functions can't be called where a value is required. A return statement that is not the last statement in a function is called an early return. Such a statement causes the function to return to the caller immediately. A function parameter is a variable used in a function where the value is provided by the caller of the function. An argument is the specific value passed from the caller to the function. When an argument is copied into the parameter, this is called pass by value. Function parameters and variables defined inside the function body are called local variables. The time in which a variable exists is called its lifetime. Variables are created and destroyed at runtime, which is when the program is running. A variable's scope determines where it can be seen and used. When a variable can be seen and used, we say it's in scope. When it cannot be seen and it cannot be used, we say it is out of scope. Scope is a compile time property, meaning it is enforced at compile time. Whitespace refers to characters used for formatting purposes. In C++, that includes spaces, tabs, and new lines. A forward declaration allows us to tell the compiler about the existence of an identifier before actually defining the identifier. To write a forward declaration for a function, we use a function prototype, which includes a function's return type, name, and parameters, but no function body, followed by a semicolon. A definition actually implements, for functions and types, or instantiates, for variables, an identifier. A declaration is a statement that tells the compiler about the existence of the identifier. In C++, all definitions serve as declarations. Pure declarations are declarations that are not also definitions, such as function prototypes. Most non-trivial programs contain multiple files. When two identifiers are introduced into the same program in a way that the compiler or linker can't tell them apart, the compiler or linker will error due to a naming collision. A namespace guarantees that all identifiers within the namespace are unique. The std namespace is one such namespace. The preprocessor is a process that runs on the code before it is compiled. Directives are special instructions to the preprocessor. Directives start with a hash symbol and end with a new line. A macro is a rule that defines how input text is converted to a replacement output text. Header files are files designed to propagate declarations to code files. When using the include directive is replaced by the contents of the included file. When including headers, use angled brackets. When including system headers, like those in C++ standard library, and use double quotes when including user-defined headers, the ones you write. When including system headers, include the versions with no .h extension if they exist. Header guards prevent the contents of a header from being included more than once into a given code file. They do not prevent the contents of a header from being included into multiple different code files. Quiz time. Okay. Write a single file program named main CPP that reads two separate integers from the user, adds them together, and then outputs the answer. Oof, I'm scared now. The program should use three functions. A function named readNumber should be used to get and return a single integer from the user. A function named writeAnswer should be used to output the answer. And this function should take a single parameter and have no return value. A main function should be used to glue the above functions together. Okay. We can do this. I just gotta think. I'm rusty, so I'm like, I guess we're in a header here. So what do we got as our main? Oh, we already have one named main CPP. Single file program, so we just need to stay here. We don't need to include add. You're fine. Get out of there. It's just like the calculator one. Adds them together. So we already have this like here. But we're using the different file. So let's close these. I'm just refreshing on syntax before I delete it. Three functions. All right. I'm laughing at how much I need to like lean to see my keyboard. I should just type. All right. I'm trying to figure out if I want to start in the main. I guess I should write the functions first, right? I'll clean it up. I will. I feel wrong. That is wrong. Whoops. If I put a comma, that would make it a declaration, right? Or semicolon, comma, oh my god. Curly brace to make it a function, right? So now we have a function called read number. Function read number can be made static. Do I want that? I was studying the syntax and now I'm like, wait, what? Character output. STD. Oh my gosh. Character output. I gotta set this down. My hands. Enter number. Do I need to do a new line? What is it? It's like that? Oh, Madison. Okay. Output. Enter number. And then. Wait, we have to. I'm trying to think. Oh my gosh. Why is this so hard? Because I'm rusty. We just kind of jumping right in. Well, I know we need this, so I'll put it in. right? Why waste time? Freaking out. I'm freaking out. Character input, I guess X. It feels, maybe? No, we need to... This feels so wrong. Int X right? It's upset though. ¿Por qué? No operator. That's not the input operator. Ah! Oh, you can't see the... I got scared. Huge, like, error tooltip popped up. Give me a moment with this for a second. I have the IO stream. Isn't input in is output? Like, why is this one fine? Character input. I need to look this up. A lot of people are saying to include string. ¿Por qué? I haven't needed to this whole time. That's weird. Let's try it. Mm-mm-mm. Mm. Move definition location. Mm-mm. What's going on? Is it this? Maybe? No. Hmm. Hmm. I don't know what's going on. Hmm. I gotta see a little example. Is it because I have spaces? Should I not have spaces? Mm. Should I not have the STD? I feel like is that okay? No. They don't like that at all. What is happening? I feel like we need to go back. I'm losing it. Mm. I want to see your turn values. Is it because I put the parentheses? I felt like it was, but then when I looked it up, everyone they didn't have it. Freaked me out. So I need to get rid of that. Thank you. I felt like the error was not, I was not relating. I felt like they were saying like, this is the wrong operator to put here. And I'm like, why? Just like calling the standard library in general. I kind of like it though. And I want it to return X. Hi. How y'all doing? I'm so rusty right now. I need to get rid of this string. See, I get nervous to like, that's why I wanted to, oh, we're back. I wanted to go into a different chapter to see what it's supposed to look like, because I was getting all kinds of different things. Okay, put my phone back up here. Okay. So I want to call this right? I'm gonna go ahead and run this and just see what the heck happens. I feel like I'm not. Wait, where are we putting X? I don't want to get too ahead. It kept saying like write a little bit and then test it. So I feel like we did that function. I don't know if we actually called it. Okay. We did it. It's close. I feel like, X. No? No, because that would be... No. I'm feeling so rusty. Just trying to think. Like, that's where I'm like, okay, we're gonna return what X is. So maybe we have too much going on here, but it's to get... I'm like... Hang on. I will get this. So right answer is going to be the actual equation function. So I feel like I just need to go like one chapter back. It's like the most recent thing. Right, so we need to initialize an X in main as well. Gotcha. And then, I feel like this needs... I'm a little lost with that. I'm like, wait. I'm gonna store read number. It's gonna return X, so I need to... Oh. I see. So we've initialized X. We have called the function. I know, I feel like there's like a much better way to do this and I've like lost it. Ooh, read line. I like that. So like right here, we can put read number. Is that gonna scare it being up here? Yeah, wait, it is a little scared. This should be above it. Or I should forward declare it. Or that is forward declaring it? Wait, cut it. Are you happy? No. Oh. I need parentheses here because it's a function. I understand. Okay. So I don't need this here at all, actually. Because we have... Yeah. Okay. All right, yeah, so this will do something now. Now it will actually call the function. Thank you. Let me run this real quick. Nah. Initialized, not referenced. Okay, yeah, because we didn't we didn't even use it for anything. Well, just run it. It doesn't like it. No. All right, never mind. So we need this, like, okay, wait. Okay. Gotcha. Actually. And then save. Build. Okay. Yay. I guess we need the output first. Ah! What? I did a G. That's not a number, so they would be upset about that. What the heck? So this, I feel like, needs to go first. Very tippy top. Honestly, that should just run like in main, right? Like, am I wrong? Read number, input, calling it, got. All right, let me try that. Oh, am I doing new line wrong? Is that the problem? Is it that? Oh my goodness. If it is that, okay. 6. Got. Let's put a space of got, but that's what I was like, what is it saying? Like, I thought it was like weird code or something. We got 6. Okay. Excellent. All right. So we're able to ask them for a number. We want this one. We want right answer to, I believe, do the adding of the numbers that are inputted. So we're going to, I think here, like inject, because we're going to do this again, but with Y. Enter another number, just so I know that it's new. Y. I'm just gonna run that. Right, and then I believe we'll do like wait. Let me start the function. Maybe. Used to output the answer. This function should take a single parameter and have no value. Have no return value. So we need void. Right? Right? Okay. But I'm like, it would be... int, right? Right? Is that right? No. Answer. Like that. Oh. Because we're going to be creating... Wait. Because I'm a little bit... I thought this was going to be doing the equation, and now I'm a little bit like, what is this even doing? I see. I understand why it's void now. That's I was like a little thrown. It's just gonna do the character output statement, and there's nothing it needs to return back to main because it's just gonna output the answer. I understand now. Thank you so much. Space between int and answer. Oh, you're right. Thank you. I understand. Okay. Right. Yeah, it's like upset. Thank you. It's gonna be just answer. That feels wrong for some reason. Oh, it's upset because I don't have answer in main. Thank you so much. Honestly, thank you. I was very stuck. This needs its own thing. Okay. do and end lines the common way. It was saying end line. I don't know. It was saying like this is more efficient because it does its own flushing or something. I don't remember. But I do feel like there needs to be like an end line somewhere, right? I don't know. All right, I know we want to do x plus y equals answer, right? Is that crazy? We have to say the answer, right? Wait. Oh. Thank you. Okay, answer is x plus y. Right? I felt like when I was starting with x plus y, I was like, this something else needs to be here. Thank you. So then the answer is this, and then we need to call function. Of right answer. Hang on, clean it up a little bit. Void. Did I call it void? Did I call it right? I'm gonna do it. Hang on. And then we're gonna get rid of this character output. Feel like that's it. Maybe. No. Okay. Hang on. Initialize but not referenced. Oh, I need to throw answer over to it. Right. Nope. It's upset. Oh, is it? Hang on. The void, you're saying? And then, hang on. This feels right. But it's giving me an error. It says right answer. This use of void is not valid. I was like, wait. Because it's like, it didn't rerun it. Oh, that's why. I was like, but wait. Yeah, okay. So let's do 6. 4. Answer's 10. Okay. I'm pretty sure that's it. How do I feel like they did go over it where like never mind. You have to put enter. Never mind. What if you didn't want to store the addition in the answer variable? Do I not want to? I wanted to have the function do the equation, but then following this outline wasn't making sense. One of the trick questions, yeah, I'm like, what? Right. Just don't even do that. Just wow. I like that better. I understand what you're saying now. Then we don't have to be hard coding an addition like that. Right? Looks happy. I do like that a lot better. Beautiful. Honestly, it was showing us to do it like that as well. I feel like readability, it makes it kind of cleaner to just see like, oh, we have 1, 2, and then they get added right there. You know? I felt like it was getting a little too much. Thank you, thank you, thank you. Let's see what the hints are. I wanted to do it without hints, and then I got a whole lot of hints. Yeah. That's true. Because I guess we are still like, I don't know. Oh, answer here. This is wrong. Wait. Wait. That needs to... No, wait. It's gonna get learned. Thank you, thank you. Really appreciate it. I think this needs to... No, wait, no. It was fine. It worked. I was getting thrown. So it's going to give it x plus y, and that information is going to be called answer. So it's going to output what it pulled there. And that's why it worked. Okay. Oh no, it's upset. I broke everything. Oh, it needed the int back. That was why. That was it. Okay. Do not need to write a separate function to do the adding. Just use the operator directly. You'll need to call read number twice. We did do that. Ooh. Whoa. Should I put the curly braces? Uh-oh. I see. Because we did the asking for the number here in main. Ooh, that's clean as heck. That was the correct answer. Thank you so much, Tarp. This was the right way to do it. All right, well, let's clean this up then. Put this up here. Pretty sure. Let's try that. Nice. Love it. Wow, that was a lot just for the first one. But now we're de-rusted for sure. Modify the program you wrote in exercise 1 so that read number and right answer live in a separate file, okay, called IOCPP. Oof. Use a forward declaration to access them from main. If you're having problems, make sure IOCPP is properly added to your project so it gets compiled. Ooh. Okay. Let's get rid of this add. Move. Remove. Add. New item. We want a new CPP file called IO. Input output. So, okay, we're gonna put these functions away. we're gonna include io.cpp. Is that right? Hello? I didn't do that. Did you find it? Did it find it? I feel like that's... Anything upset? No. Uh-oh. It's upset. It did not like... Oh, because... Hang on. No, I did not compile this one. Which they're supposed to compile together, but I don't know. Dang it. Okay, so these are linking errors. Did I write io dot, like the, did I do the includes right? Yeah, looks right. Do I need to do the header instead? No, because the next one's for the header file. Uh-oh. That's what's wrong. Hang on. Wait, right? No, we're fine. Excuse me. Did not mean to cough into the mic. It's already defined in here. See, I think what will really get us better is knowing what most of these errors mean. It's already defined. Where? Like, I get... in IO, but like, where? We need to call the function declaration. Beep bop, boop boop, beep bop. Good lord. I think we don't need to have that. Ow. Now I'm confused. No. What? Save. Save. Just do it. Oh my god, dude. I feel like maybe I have forward declared this wrong. They don't need this, right? Or maybe I'm wrong. They're like, bitch. Put it back, bitch. Okay. Let's look at multiple files. Nope, nope. Forward declarations. Boop, 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 boop. Do I need to say like in and excuse me, void? That nope, it really is upset. It's mad at me. Oh, because right answer is going to be an int and an int. Right? Just maybe it's all over the place. No warnings? No. It's already defined. This needs that. Going all over the place. Just anything that'll work. int x, int y. This feels crazy. I don't feel like we need this. I'm losing it. Or maybe we do. Like, it should just call the function. And I think that's why it's saying it's like too few arguments in function call. I did do stuff over here. No. Let's go to multiple files. Wait, is it because I included maybe? Wait, I need it. I need it here. Hang on. Why have we broken it just by moving it around a little? Needed so that main knows that add is a function defined elsewhere. Can I just like... Right? Like, what's wrong with that? Right answer. Seems like right answer is the biggest issue. Maybe this is what the problem is. No. So we need to inject this. Maybe just call it X. Okay. So this needs to be int x, comma. I'm so confused. But why? Why? We're writing the answer. And then it should just be Void. Right answer. Okay. And now. Oh. How do I know that these are actually... I mean, yeah, it should be. Should I get rid of the int? No, because it needs information injected. I'm gonna get this. Needed so that main knows the add is a function defined elsewhere. So it's saying like it's already defined, and I'm like, I know. Good. It should be defined there. Am I defining it here? Am I not? Am I not doing this right? It's different than the implementation. Because it needs to be like... I mean, it felt like we just tried this, but then I was still upset, but... That feels so wrong. I felt like... I feel like we should just have the int. Well, no, yeah, wait. I'm lost. It takes two and then it adds it. And so in my head, it makes it become one int, right? After it adds it, it's throwing just one integer to the function. Oh. Wait. Is that what it needs? It wants that? Maybe? Hello. Oh my god, still no. What's up? Mm. Anything else on the file? Just this. What's the problem? I feel like I've made it like a mess trying to figure this out. So we're doing a quiz, I guess. So right here it's asking us to call .cpp, and then the next one we're going to be making a header and calling the header instead. It's like I can't even get it to get this .cpp working. But part of me does feel like they're not linking right, or they're not, I don't know. I mean, clearly they aren't. No. Please, I will take all the help I will get. That's what I was feeling like. Oh, this isn't working because I need to make it be a header instead. And I was like, wait. Next one, we need to do IO header. I don't know why it's upset. It keeps saying already defined an IO object. Is it because I have the IO stream here? Is that all it is? Hang on. Wait, because it's gonna be upset. It needs it. So yeah, maybe it'll be I'm like, maybe it'll be fine without it. I'm like, I feel like it still needs it. But I guess it's running the function. So yeah, that might be the problem. It's so upset. It's so mad. Still upset. So yeah, we got include Is that the problem? I guess. Wait. I don't know. Move line 2 to 13. Remove it? Just need a declaration. These are the declarations here. It's open. So I think I understand now. Because it's still in the file, like in the Hello World source files, I didn't need to do the includes where it's copy and pasting. When I asked for the function, when I forward declared it, it's going to look through all the source files for that function, and it will find it in io.cpp. And that's why I was like, it's already defined here. Why are you defining it again? That's why I was like confused. It's saying like, it's already defined here. I'm like, yeah, I know, that's where I want it defined. I feel like the way it was giving me the error was really throwing me off. Thank you. You fixed it. 5 and 7, 12. Beautiful, beautiful. Okay. So now the header file is going to be this. I understand now. Header files. Add. New item. We want it to be a header file called IO. Add. I don't remember what the Pragma wants. I don't remember what the header guards are that they recommended, but they also said that Pragma once was acceptable. And then now this would be include io.header. Okay. I don't think I need to compile all of them, but I feel like I have to sometimes. And it still works. Beautiful. Thank you so much. What's up? Modify so that we have .cpp. We just need to use a forward. To me, I was thinking that the include was a forward declaration. And then I also was doing a forward declaration as well. Header, access the functions instead of using forward declarations directly in your code. Make sure your header file uses header guards. I do want to see what like the good header guard is. You compile your program and get errors like this one. I did not. You probably forgot to include io.cpp in your project. They were. Okay. This is if not defined, and it has to be all caps as well. I forgot about that. And instead of dot, it's underscore. We need to remember that. Okay, so we got read number, right answer in X, love that. And then io.cpp. We didn't need to include the header. Is that... Why? I feel like that would cause like a weird... I guess that's the guard. If it's been defined, right? Oh. Okay, and then the main should look... Oh, main. Whoa. Oh, we didn't need to add the IO stream into main. Interesting. Oh. Because we only needed the input and output here. Very interesting. Well, technically, io.cpp doesn't require the inclusion of IO. That's what I'm confused. It's best practice for code files to include their paired header files. This is covered. I was thinking about that when I was looking at it. I was like, why? It's going to cause a loop, but then the header guard keeps us from doing anything. Like it was included here, so this is more just so it's linked up. Like readability. Wow, that was a lot. Definitely want to take a break. And then I think we should go in on 3.1. Semantics errors. Whoa. Okay. Yeah. I think we need to do a break after that because it was a lot. Thank you so much to everyone here, everyone helping. I would have probably still sitting here like, but we got it. We got it. All right, I will be back shortly. Thank you. I'm back. Okay. Getting a little sleepy, but I have my mocha. So I'm going to keep it right here. Easy access. Okay. .1 Syntax and semantic errors. Back into the reading, guys. We got this. That was so much, and it was so good. I feel like I learned so much. Software errors are prevalent. It's easy to make them, and it's hard to find them. In this chapter, we'll explore topics related to the finding and removal of bugs within our C++ programs. We literally just did that. Including learning how to use the integrated debugger that is part of our IDE. Although debugging tools and techniques aren't part of the C++ standard, learning to find and remove bugs in the programs you write is an extremely important part of being a successful programmer. Therefore, we'll spend a bit of time covering such topics, so that as the programs you write become more complex, your ability to diagnose and remedy issues advances at a similar pace. Let me turn the air filter off. I don't know if that's causing any background noise. Volume down. I'll speak up. This song is loud. We'll just skip this one. That one, I think you constantly ask for that to be turned down, and then everything else is too quiet after, because that one is too loud. We're good now. Okay. Yes. If you have experience debugging programs in another programming language, much of this will be familiar to you. Definitely have had to do this with like HTML. Which I know is like, I don't know. It's not really bugs that you're dealing with, you know? Syntax errors. Programming can be challenging, and C++ is somewhat of a quirky language. It's a little quirky. Put those two together, and there are a lot of ways to make mistakes. Errors generally fall into one of two categories: syntax errors and semantics errors, logic errors. A syntax error occurs when you write a statement that is not valid according to the grammar of the C++ language. This includes errors such as missing semicolons, mismatched parentheses or braces, etc. For example, the following program contains quite a few syntax errors. Missing closing brace. Variable name can't start with a number, right? Hi there, semicolon in the middle of some shit. Extraneous semicolon. Operator, injection operator does not exist. Missing semicolon at the end of statement. Wow. Fortunately, the compiler will detect syntax errors and issue a compilation warning or error, so you easily identify and fix the problem. Then it's just a matter of compiling again until you get rid of all the errors. I am going to take that acid. Too much coffee. I have to, now that I've been diagnosed with asthma, I have to keep an eye on my acid because that can trigger asthma. It's crazy. Okay. Semantic errors. A semantic error is an error in meaning. These occur when a statement is syntactically valid, but either violates other rules of the language or does not do what the programmer intended. Some kind of semantic errors can be caught by the compiler. Common examples include using an undeclared variable, type mismatches, when we use an object with the wrong type somewhere, etc. For example, the following program contains several compile time semantic errors. X not declared cannot assign a value to 5, right? We need to flip it. X equals 5. We have learned this from chat. Thank you, chat. Return hello. Hello cannot be converted to an int. Interesting. As it needs to return 0. Int main. Return 0. Understand. Other semantic errors only manifest at runtime. Sometimes these will cause your program to crash, such as in the case of division by 0. Division by 0 is undefined in mathematics. Like, literally in real life, we can't do this, so stop it. Okay. More often, these will just produce the wrong value or behavior. No initializer provided. Use of uninitialized variable leads to undefined result. Okay. Or this function is supposed to perform addition, but it doesn't due to the wrong operator being used. Yeah, I mean, should produce 8 but produces 2. Oh, because it's saying add, it's called add, but then it's actually subtracting. Or function returns here, return 0. So this never, yeah. Like, this is where it ends. So this never executes, okay. In the above example, the errors are fairly easy to spot, but in most non-trivial programs, runtime semantics errors are not easy to find by eyeballing the code. This is where debugging techniques can come in handy. Okay. Let's say you've written a program and it's not working correctly. Oh, sorry. 3.2, the debugging process. Let's say you've written a program and it's not working correctly. The code compiles fine, but when you run it, you're getting an incorrect result. You must have a semantic error somewhere. How can you find it? If you've been following best practices by writing a little bit of code and then testing it, you may have a good idea where your error is. Or you may have no clue at all. All bugs stem from a simple premise. Something that you thought was correct isn't. Actually, yeah, that is, yeah. Actually figuring out where that error is can be challenging. In this lesson, we'll outline the general process of debugging a program. Because we haven't covered that many C++ topics yet, our example programs in this chapter are going to be pretty basic. Excuse me. That may make some of the techniques we're showing here seem excessive. However, keep in mind that these techniques are designed to be used with larger, more complex programs, and will be of more use in such a setting, which is where you need them most. A general approach to debugging. Once a problem has been identified, debugging the problem generally consists of 6 steps. Find the root cause of the problem, usually the line of code that's not working. We'll discuss some strategies on how to do this in the next lesson. 2. Ensure you understand why the issue is occurring. 3. Determine how you'll fix the issue. 4. Repair the issue causing the problem. 5. Retest to ensure the problem has been fixed. 6. Retest to ensure no new problems have emerged. Let's use a real-life analogy here. Let's say one evening you go to get some ice from the ice dispenser in your freezer. You put your cup up to the dispenser, press the lever, and nothing comes out. Uh-oh. You've discovered some kind of defect. What would you do? You probably start an investigation to see if you can identify the root cause of the issue. Find the root cause. Since you hear the ice dispenser trying to deliver ice, it's probably not the ice delivery mechanism itself, so you open the freezer and examine the ice tray. No ice. Is that the root cause of the issue? No, it's another symptom. After further examination, you determine that the ice maker does not appear to be making ice. Is the problem the ice maker or something else? The freezer is still cold, the water line isn't clogged, and everything else seems to be working, so you conclude that the root cause is that the ice maker is non-functional. Understand the problem. This is a simple case. A broken ice maker won't make ice. Determine a fix. At this point, you have several options for a fix. You could work around the issue, buy a bag of ice from a store. You could try to diagnose the ice maker further, see if there's a part that can be repaired. You could buy a new ice maker and install it in place of the current one. Or you could buy a new freezer. You decide to buy a new ice maker. Repair the issue. Once the ice maker has arrived, you install it. Retest. After turning the electricity back on and waiting overnight, your new ice maker starts making ice. No new issues are discovered. Now, let's apply this process to our simple program from the previous lesson. This function is supposed to perform addition, but it doesn't due to the wrong operator being used. Should produce 8, but it produces 2. This code is nice in one regard. The bug is very apparent. Because the wrong answer gets printed to the screen via line 10, that gives us a starting point for our investigation. Find the root cause. On line 10, we can see that we're passing in literals for arguments, 5 and 3. So there is no room for error there, since the inputs to function add are correct. But the output isn't. It's pretty apparent that function add must be producing the wrong value. The only statement in function add is the return statement, which must be the culprit. We found the problem line. Now that we know where to focus our attention, noticing that we're subtracting instead of adding is something you're likely to find via inspection. Excuse me. Understand the problem. In this case, it's obvious why the wrong value is being generated. We're using the wrong operator. Determine a fix. We'll simply change operator minus to operator plus. Repair the issue. This is actually changing operator minus to plus and ensuring the program recompiles. Retest. After implementing the change, rerunning the program will indicate that our program now produces the correct value of 8. For the simple program, that's all the testing that's needed. This example is trivial, but illustrates the basic process you'll go through when diagnosing any program. Let's do it. 3.3, a strategy for debugging. Excuse me. When debugging a program, in most cases, the vast majority of your time will be spent trying to find where the error actually is. Once the issue is found, the remaining steps, fixing the issue and validating that the issue was fixed, are often trivial in comparison. In this lesson, we'll start exploring how to find errors. Finding problems via code inspection. Let's say you've noticed a problem, and you want to track the cause of that specific problem down. In many cases, especially in smaller programs, we can approximate where the issue is likely to be based on the nature of the error and the way the program is structured. Consider the following program snippet. Ask the user to enter a bunch of names, sort them in alphabetical order, print the sorted list of names. Okay. If you expected this program to print the names in alphabetical order, but it printed them in opposite order instead, the problem is probably in the sort names function. In cases where you can narrow down the problem down to a specific function, you may be able to spot the issue just by looking at the code. However, as programs get more complex, finding issues by code inspection becomes more complex as well. First, there's a lot more code to look at. Looking at every line of code in a program that is thousands of lines long can take a really long time, not to mention it's incredibly boring. Second, the code itself tends to be more complex, with more possible places for things to go wrong. Third, the code's behavior may not give you many clues as to where things are going wrong. If you wrote a program to output stock recommendations and it actually output nothing at all, you probably wouldn't have much of a lead on where to start looking for the problem. Finally, bugs can be caused by making bad assumptions. It's almost impossible to visually spot a bug caused by a bad assumption, because you're likely to make the same bad assumption when inspecting the code and not notice the error. So, I'm like, that's literally the problem we are having. So, if we have an issue that we can't find by code inspection, how do we find it? Finding problems by running the code. Fortunately, if we can't find an issue via code inspection, there is another avenue we can take. We can watch the behavior of the program as it runs and try to diagnose the issue from that. This approach can be generalized as 1. Figure out how to reproduce the problem. 2. Run the program and gather information to narrow down where the problem is. 3. Repeat the prior step until you find the problem. For the rest of this chapter, we'll discuss techniques to facilitate this approach. Reproducing the problem. The first and most important step in finding a problem is to be able to reproduce the problem. Reproducing the problem means making the problem appear in a consistent manner. The reason is simple. It's extremely hard to find an issue unless you can observe it occurring. Back to our ice dispenser analogy, let's say one day your friend tells you that your ice dispenser isn't working. You go look at it and it works fine. How would you diagnose the problem? It would be very difficult. However, if you could actually see the issue of the ice dispenser not working, then you could start to diagnose why it wasn't working much more effectively. If a software issue is blatant, like the program crashes in the same place every time you run it, then reproducing the problem can be trivial. However, sometimes reproducing an issue can be a lot more difficult. The problem may only occur on certain computers or in particular circumstances, like when the user enters certain input. In such cases, generating a set of reproduction steps can be helpful. Reproduction steps are a list of clear and precise steps that can be followed to cause an issue to recur with a high level of predictability. The goal is to be able to cause the issue to reoccur as much as possible, so we can run our program over and over and look for clues to determine what's causing the problem. If the issue can be reproduced 100% of the time, that's ideal, but less than 100% reproducibility can be okay. An issue that occurs only 50% of the time simply means it'll take twice as long to diagnose the issue, as half the time the program won't exhibit the problem, and thus not contribute any useful diagnostic information. I don't know if it's not any. Oh, it won't contribute any while it's working. I see. I was like, even if it's half the time, it's still contributing. Or twice the time, I mean. I don't know if I've heard this one yet. Okay. Homing in on issues. Once we can reasonably reproduce the problem, the next step is to figure out where in the code the problem is. Based on the nature of the problem, this may be easy or difficult. For the sake of example, let's say we don't have much of an idea where the problem actually is. How do we find it? An analogy will serve us well here. Let's play a game of high-low. I'm going to ask you to guess a number between 1 and 10. For each guess you make, I'll tell you whether each guess is too high, too low, or correct. An instance of this game might look like this. 5, too low. 8 is too high. 6 is too low. 7 is the right number. In the above game, you don't have to guess every number to find the number I was thinking of. Though the process of making guesses and considering the information you learn from each guess can home in on the correct number with only a few guesses. If you use an optimal strategy, you can always find the number I'm thinking of in 4 or fewer guesses. We can use a similar process to debug programs. In the worst case, we may have no idea where the bug is. However, we do know that the problem must be somewhere in the code that executes between the beginning of the program and the point where the program exhibits the first incorrect symptom that we can observe. That at least rules out, sorry, I'm like, what? That at least rules. That at least rules out the parts of the program that execute after the first observable symptom. But that still potentially leaves a lot of code to cover. To diagnose the issue, we'll make some educated guesses about where the problem is, with the goal of homing in on the problem quickly. Often, whatever it was that caused us to notice the problem will give us an initial guess that's close to where the actual problem is. For example, if the program isn't writing data to a file when it should be, then the issue is probably somewhere in the code that handles writing to a file. Duh. Then we can use a high-low strategy to try and isolate where the problem actually is. For example, if at some point in our program we can provide that the problem has not yet occurred, this is analogous to receiving a too low, high-low result. We know the problem must be somewhere later in the program. For example, if our program is crashing in the same place every time, and we can prove that the program has not crashed at a particular point in the execution of the program, then the crash must be later in the code. Right? Okay. If at some point in our program we can observe incorrect behavior related to the problem, then this is analogous to receiving a too high, high-low result. And we know the problem must be somewhere earlier in the program. For example, let's say a program prints the value of some variable x. You're expecting it to print value 2, but it printed 8 instead. Variable x must have the wrong value. If at some point during the execution of our program we can see that the variable x already has value 8, then we know the problem must have occurred before that point. The high-low analogy isn't perfect. We can also sometimes remove entire sections of our code from consideration without gaining any information on whether the actual problem is before or after that point. We'll show examples of all 3 of these cases in the next lesson. Eventually, with enough guesses and some good technique, we can home in on the exact line causing the problem. Sorry, exclamation point. If we made any bad assumptions, this will help us discover where. When you've excluded everything else, the only thing left must be causing the problem. That's Sherlock Holmes, right? Then it's just a matter of understanding why. What guessing strategy you want to use is up to you. The best one depends on what type of bug it is. So you'll likely want to try many different approaches to narrow down the issue. As you gain experience in debugging issues, your intuition will help guide you. Wow. So how do we make guesses? There are many ways to do so. We're going to start with some simple approaches in the next chapter. Then we'll build on these and explore others in future chapters. Okay. 3.4. Basic debugging tactics. Oh, let's do a Maddie check-in. How are you? Oh. She's been so baby today. Sleepy.
Maddie wanted attention.
Hey, sleepy girl. Oh. Okay. That was your Maddie check-in for the hour. Okay. Let's get some water. How we doing, chat? All right. 3.4. Basic debugging tactics. In the previous lesson, we explored a strategy for finding issues by running our programs and using guesswork to home in on where the problem is. In this lesson, we'll explore some basic tactics for actually making those guesses and collecting information to help find issues. Debugging tactic number 1, commenting out your code. Let's start with the easy one. If your program is exhibiting erroneous behavior, one way to reproduce the amount of code you have to search through is to comment some code out and see if the issue persists. If the issue remains unchanged, the commented out code probably wasn't responsible. Consider the following code. I really need to add consider the following. Ask the user to enter a bunch of names, do some random stuff, sort them in alphabetical order, print a sorted list of names. Okay. Let's say this program is supposed to print the names the user enters in alphabetical order, but it's printing them in reverse alphabetical order. Where's the problem? Is get names entering the names incorrectly? Is sort names sorting them backwards? Is print names printing them backwards? It could be any of those things, but we might suspect do maintenance has nothing to do with the problem, so let's comment it out. Okay. There are 3 likely outcomes. If the problem goes away, then do maintenance must be causing the problems, and we should focus our attention there. If the problem is unchanged, which is more likely, then we can reasonably assume that do maintenance wasn't at fault, and we can exclude the entire function from our search for now. It doesn't help us understand whether the actual problem is before or after the call to do maintenance, but it reduces the amount of code we have to subsequently look through. If commenting out do maintenance causes the problem to morph into some other related problem, like the program stops printing names, then it's likely that do maintenance is doing something useful that some other code is dependent on. In this case, we probably can't tell whether the issue is in do maintenance or elsewhere, so we can uncomment do maintenance and try some other approach. Warning. Don't forget which functions you've commented out so you can uncomment them later. After making many debugging related changes, it's very easy to miss undoing 1 or 2. If that happens, you'll end up fixing one bug but introducing others. Having a good version control system is extremely useful here, as you can diff your code against the main branch to see all the debugging related changes you've made and ensure that they are reverted before you commit your change. Tip: an alternate approach to repeatedly adding, removing, or commenting debug statements is to use a third-party library that will let you leave debug statements in your code but compile them out in release mode via a preprocessor macro. DBG is one such header-only library that exists to help facilitate this via the DBG macro disable preprocessor macro. We discuss header-only libraries in lesson 7.9, inline functions and variables. I feel like we've seen chapter 7 is going to be crazy, right? Debugging tactic number 2, validating your code flow. Another problem common in more complex programs is that the program is calling a function too many or too few times, including not at all. In such cases, it can be helpful to place statements at the top of your functions to print Let's bring it back. Okay. In such cases, it can be helpful to place statements at the top of your functions to print the function's name. That way, when the program runs, you can see which functions are getting called. Tip: when printing information for debugging purposes, use standard SIR instead of standard character output. Interesting. One reason for this is that character output may be buffered, which means a bit of time may pass between when you ask character output to output text when it actually does. If you output using character output and then your program crashes immediately afterward, character output may or may not have actually output yet. This can mislead you about where the issue is. On the other hand, standard SIR is unbuffered, which means anything you send to it will output immediately. Okay. This helps ensure all debug output appears as soon as possible, at the cost of some performance, which we usually don't care about when debugging. Using SIR also helps make clear that the information being output is for an error case rather than a normal case. We discuss when to use character output versus SIR further in lesson 9.4. Detecting and handling errors. So fun. Okay. Consider the following. Consider the following simple program that doesn't work correctly. Okay. You may need to disable treat warnings as errors for the above to compile. Although we expect this program to print the value 4, it should print the value 1. On Visual Studio and possibly some other compilers, it may print the following instead. Yeah, why? Related content. We discuss why some compilers print 1 versus an address, and what to do if your compiler prints 1, but you want it to print an address in lesson 20.1, function pointers. Wow, okay. Let's add some debugging statements to these functions. Okay, SIR. Weird. Oh, we're indicating like output that main called. Main got called, get value got called. Tip: when adding temporary debug statements, it can be helpful to not indent them. This makes them easier to find for removal later. If you're using Clang format to format your code, it will try to auto-indent these lines. You can suppress the automatic formatting like this. Okay. Now, when these functions execute, they'll output their names, indicating that they were called. Main was called. Now we can see that function getValue was never called. Oh, is that why? But wait, yeah, why were you? Oh, because we didn't add the parentheses, right? That makes it a function. We debugged it. GetValue is never called. There must be some problem with the code that calls the function. Let's take a closer look at that line. Oh look, we forgot the parentheses on the function call. It should be added parentheses here. This will now produce the correct output. Love it. And we can remove the temporary debugging statements. Debugging tactic 3, printing values. With some types of bugs, the program may be... Hello? It said battery low. No, we're gonna have to be without music for a bit. Well, you guys won't be. I will be. But I think it gives me some time. Printing values. With some types of bugs, the program may be calculating or passing the wrong value. We can also output the value of variables, including parameters or expressions, to ensure that they are correct. Consider the following program that is supposed to add two numbers but doesn't work correctly. X and 5. X is never defined, right? Is that the... Get user from... Okay, X is this. Man. Okay, I don't know. Here's some output from this program. Enter a number. 4. Enter number 3. The answer's 9. Yeah, what the heck? Flying through it, are we? Hope so. That's not right. Do you see the error? Even in this short program, it can be hard to spot. Let's add some code to debug our values. Oh. Main. Yeah. Here's the above output. 4, 3, Z is 9. So where is Z coming from? Like, where is add X plus 9? Yeah. This was what was throwing me. I was like, that don't look right. So 3. Okay, so yeah, X was just 4 plus 5. Yeah. Weird. Variables X and Y are getting the right values, but variable X or Z isn't. The issue must be between those 2 points, which makes function add a key suspect. Let's modify function add. Is that the issue? Okay. Add was called. Now we'll get the output. Yeah, so it says it was called, it got Y and 5. Main is calling Z is 9. Variable Y had a value 3, but somehow our function add got the value 5 for parameter Y. We must have passed the wrong argument. Sure enough. So that 5 needs to just be a Y, is all. There it is. We passed the literal 5 instead of the value of variable Y as an argument. That's an easy fix, and then we can remove the debug statements. One more example. Hang on, I gotta get crisscrossed. Hopefully. Hang on. Lollipop while I do. My ass was falling asleep. Y'all okay? Give me a moment. One more example. This program is very similar to the prior one, but also doesn't work like it should. I've been buffering this whole stream.
Rats, where rats, where the rats?
That's how I feel with this lollipop. And I was like, I have to be a rat. It's very tasty. Mm. What the heck? That's got to be what it is. Like what? If we run this code, we see the following. 4, 3, the answer is 5. Something is wrong, but where? Let's instrument this code with some debugging. Add got called. Output what the got. Print result was called. Answer that got. This is like full. Now let's run the program again with the same inputs. Main's called. Get user inputs called. Number entered is 4. X equals 3. Get user input called. 3. Yeah, like this should be 4 though. This should be 3. So because it is subtracting. Now we can immediately see something's going wrong. The user is entering the value 4, but main's X is getting value 3. Something must be going wrong between where the user enters input and where that value is assigned to main's variable X. Let's make sure that the program is getting the correct value from the user by adding some debug code to function getUserInput. And the output. We've died. We are dead. Let him charge. But now I have to, excuse me. I have to hear myself. Not in my own head. Alright. Give me a moment. Okay. Main got called because like this is wait 4 4 3 3 3 and then 2. This is sorry, I'm just like a little like what? This additional line of debugging, we can see that the user input is received correctly into getUserInput's variable X. And yet somehow main's variable X is getting the wrong value. The problem must be between those 2 points. The only culprit left is the return value from function getUserInput. Let's look at that line more closely. Why? That's odd. What's that double minus symbol before X? We haven't covered that yet in these tutorials, so don't worry if you don't know what it means. But even without knowing what it means, through your debugging efforts, you can be reasonably sure that this particular line is at fault. And thus, it's likely this double minus symbol is causing the problem. Since we really want get user input to return just the value of x, let's remove the double minus and see what happens. It should work. Moved it. Beautiful. The program is now working correctly. Even without understanding what the double minus was doing, we were able to identify the specific line of code causing the issue and then fix the issue. Why using printing statements to debug isn't great. While adding debugging statements to programs for diagnostic purposes is a common rudimentary technique and a functional one, especially when a debugger is not available for some reason, it's not that great for a number of reasons. Debug statements clutter your code. Debug statements clutter the output of your program. Debug statements require modification of your code to both add and to remove, which can introduce new bugs. Debug statements must be removed after you're done with them, which makes them non-reusable. We can do better. We'll just explore how in future lessons. That's so fun. Okay. Let's take a sippy. I don't know if I like the cafe mocha. Like maybe I do, but just want a cold brew, you know. Let me get some water. Okay. I want my lollipop. I'm having a good time with it. It was worth the 29 cents. 3.5. More debugging tactics. In the previous lesson, 3.4, Basic Debugging Tactics, we started exploring how to manually debug problems. In that lesson, we offered some criticisms of using statements to print debug text. 1. Debug statements clutter your code. 2. Debug statements clutter the output of your program. 3. Debug statements require modification of your code, both to add and to remove, which can introduce new bugs. 4. Debug statements must be removed after you're done with them, which makes them non-reusable. We can mitigate some of these issues. In this lesson, we'll explore some of the basic techniques for doing so. Conditionalizing your debugging code. Consider the following program that contains some debug statements. When you're done with the debugging, I don't see, I guess main was called, function was called. When you're done with the debugging statement, you'll either need to remove them or comment them out. Then, if you want them again later, you'll have to add them back or uncomment them. One way to make it easier to disable and enable debugging throughout your program is to make your debugging statements conditional using preprocessor directives. Ooh. Oh. Interesting. If it's enabled. Oh my god, I love that. Ah, I love it. I love it. I love it. Okay. Now we can enable debugging simply by commenting, uncommenting, define, enable debug. I'm gonna go into debug mode. Oh my god, I get it now. This allows us to reuse previously added debug statements and then just disable them when we're done with them, rather than having to actually remove them from the code. If this were a multi-file program, the define enable debug will go in a header file that's included into all code files, so we can comment, uncomment the define in a single location and have it propagate to all code files. This addresses the issue with having to remove debug statements and the risk in doing so, but at the cost of even more code clutter. Another downside of this approach is that if you make a typo, misspell debug, or forget to include the header into a code file, some or all of the debugging for that file may not be enabled. So although this is better than the unconditionalized version, there's still room to improve. Oh my god, don't tell me that. Using a logger. An alternative approach to conditionalized debugging via the preprocessor is to send your debugging information to a log. Oh my gosh. A log is a sequential record of events that have happened, usually time-stamped. Drugs. I can't hear it either. I hope you guys can hear it. I hope it's a good volume. Maybe I should have it up a little bit so I can hear slightly what's going on. Just make sure the mic isn't picking it up. Did it not play? Did it? I need to hear it.
Must be on drugs.
All right, we got it. Okay. Okay, log file. I'm a little bit like, do I need my inhaler? Like, I feel like I'm taking a long time to like fill my lungs. Oh my goodness. Toasty is all messed up. What the heck? Why is he so small? That was weird. Also, I don't know how to stop this from happening with Toasty, but it's funny though. So I don't really mind. Process of generating a log is called logging. Typically, logs are written to a file on disk called a log file, so they can be reviewed later. Most applications and operating systems write log files so they can be used to help diagnose issues that occur. Log files that have a few advantages. Log files have a few advantages. Because the information written to a log file is separated from your program's output, you can avoid the clutter caused by mingling your normal output and debug output. What? Okay. Log files can also be easily sent to other people for diagnosis. So if someone's using your software, has an issue, you can ask them to send you the log file, and it might help give you a clue where the issue is. C++ contains an output stream named standard clog, CLOG, that is intended to be used for writing logging information. However, by default, standard CLOG writes to the standard error stream, same as standard C error. I was like, sir? Okay, CLOG, C error. And while you can redirect it to file instead, this is one area where you're generally better off using one of the many existing third-party logging tools available. Which one you use is up to you. For illustrative purposes, we'll show what outputting to a logger looks like using the plog logger, plog logger. Plog is implemented as a set of header files, so it's easy to include anywhere you need it. And it's lightweight and easy to use. Interesting. Plog. include the logger headers, initializers, rolling field initializer header, plog. Okay. Here's the output from the above logger in the log file.txt file. Debug. Okay. No more crisscross. How you include, initialize, and use a logger will vary depending on the specific logger you select. Note that conditional compilation directives are also not required using this method, as most loggers have a method to eliminate writing output to the log. Okay. This makes the code a lot easier to read, as the conditional compilation lines add a lot of clutter. Hello? Nedster. Oh my god. Nedster. Here you go. Welcome. Where were we? This makes the code a lot easier to read, as the conditional compilation lines adds a lot of clutter. With plog, logging can be temporarily disabled by changing the init statement to the following. Eliminates writing of most messages, essentially turning logging off. Okay. We won't use plog in any future lessons, so you don't need to worry about learning it. I love that. As an aside, if you want to compile the above example yourself or use plog in your own projects, you can follow these instructions to install it. First, get the latest plog release. Visit the plog repo. Click the green code button in the top right corner and choose Download Zip. Next, unzip the entire archive to somewhere on your hard drive. Finally, for each project, set the somewhere plog master include directory as an include directory inside your IDE. There are instructions on how to do this for Visual Studio here and code blocks here. Since plog doesn't have a compiled library file, you can skip the parts related to precompiled library files. The log file will generally be created in the same directory as your executable. Tip: in larger or performance-sensitive projects, faster and more feature-rich loggers may be preferred, such as Speedlog. Ooh. Okay. 3.6. Using an integrated debugger. Stepping. We stepping. When you run your program, execution begins at the top of the main function and then proceeds sequentially statement by statement until the program ends. At any point in time while your program is running, the program is keeping track of a lot of things. The value of the variables you're using, which functions have been called so that when those functions return, the program will know where to go back to, and the current point of execution within the program, so it knows which statement to execute next. All of this tracked information is called your program state, or just state for short. In previous lessons, we explored various ways to alter your code to help with debugging, including printing diagnostic information or using a logger. These are simple methods for examining the state of a program while it's running. Although these can be effective if used properly, they still have downsides. They require altering your code, which takes time and can introduce new bugs, and they clutter your code, making the existing code harder to understand. Behind the techniques we've shown so far is an unstated assumption that once we run the code, it will run to completion, only pausing to accept input. with no opportunity for us to intervene and inspect the results of the program at whatever point we want. However, what if we were able to remove this assumption? Fortunately, most modern IDEs come with an integrated tool called a debugger that is designed to do exactly this. The debugger. A debugger is a computer program that allows the program to control how another program executes and examine the program state while the program is running. For example, the programmer can use a debugger to execute a program line by line, examining the value of variables along the way. By comparing the actual value of variables to what is expected, or watching the path of execution through the code, the debugger can help immensely in tracking down semantic logic errors. The power behind a debugger is twofold: the ability to precisely control execution of the program, and the ability to view and modify, if desired, the program's state. Initially, debuggers, such as GDB, were separate programs that had command line interfaces, where the programmer had to type arcane commands to make them work. Later debuggers, such as early versions of Borderlands Turbo Debugger, Borderlands, oh my god, Borderlands, I was like, what? I'm so confused. We're still separate programs, but supplied a graphical front end to make working with them easier. These days, many modern IDEs have an integrated debugger. That is, a debugger that uses the same interface as the code editor, so you can debug using the same environment that you use to write your code, rather than having to switch programs. While integrated debuggers are highly convenient and recommended for beginners, command line debuggers are well supported and still commonly used in environments that do not support graphical interfaces, embedded systems. Nearly all modern debuggers contain the same standard set of basic features. However, there is little consistency in terms of how the menus to access these features are arranged, and even less consistency in the keyboard shortcuts. Although our examples will use screenshots from Microsoft Visual Studio and will cover how to do everything in CodeBlock as well, you should have little trouble figuring out how to access each feature we discuss, no matter which IDE you're using. Tip: Debugger keyboard shortcuts will only work if the IDE integrated debugger is the active window. Okay. The remainder of this chapter will be spent learning how to use the debugger. Okay. Tip: don't neglect learning to use a debugger. As your programs get more complicated, the amount of time you spend learning to use the integrated debugger effectively will pale in comparison to the amount of time you save finding and fixing issues. Okay? Warning: before proceeding with this lesson and subsequent lessons related to using a debugger, make sure your project is compiled using a debug build configuration. You're compiling your project using a release configuration instead. The functionality of the debugger, I see, we're here in debug, may not work correctly. When you try to step into your program, it will just run the program instead. Okay. We're gonna skip CodeBlock stuff because I ain't got time for that. For Visual Code, we're not Visual Code. Visual Studio, right? We're in debugging, right? Stepping. We're going to start exploration of the debugger by first examining some of the debugging tools that allow us to control the way a program executes. Stepping is the name for a set of related debugger features that let us step through our code statement by statement. Oh, okay. There are a number of related stepping commands that we'll cover in turn. step into. The step into command executes the next statement in the normal execution path of the program and then pauses execution of the program so we can examine the program state using the debugger. If the statement being executed contains a function call, step into causes the program to jump to the top of the function being called, where it will pause. Let's take a look at a very simple program. Okay. Let's debug this program using the step into command. First, locate and then execute the step into debug command once. What? Visual Studio, the step into command can be accessed via debug menu, step into, oh, or F11. Fun. Ah. Oh, I'm scared. Ah. Oh my gosh. We're debugging. We're stepping into it. Now what? Alright, I'm gonna close it. F11. We know F11. Let me out. Okay. Hello? I've kinda... Oh. There's a stop button. Ah. Continue. Ooh. Top right of continue. Wait, what? I see it. I see it there. Thank you. Not the fire button. Please don't press the fire button. Oh my god. Okay. Okay, we did F11. Your program isn't... Wait. Visual Studio. We're good. Okay. When your program isn't running and you execute the first debug command, you may see quite a few things happen. I did. The program will recompile if needed. The program will begin to run. Because our application is a console program, a console output window should open. It will be empty because we haven't output anything yet. Your IDE may open some diagnostic windows, which may have names such as diagnostic tools, call stack, and watch. We'll cover what some of these are later. For now, you can ignore them. Because we did a step into, you should now see some kind of marker appear to the left. I did see that. Opening brace of function main, line 9. In Visual Studio, this marker is a yellow arrow. If you're using a different IDE, you should see something that serves the same purpose. This guy. This arrow marker indicates that the line being pointed to will be executed next. In this case, the debugger is telling us that the next line to be executed is the opening brace of function main, line 9. Choose step into using the appropriate command for your IDE listed above to execute the opening brace, and the arrow will move to the next statement, line 10. Okay. So it's going to start at main, and then you say next, and then if it's going to call this function, it's going to jump up to 3. That is actually really helpful to see like where it's moving. We're stepping into it. This means the next line that will be executed is the call to function print value. Choose step into again because this statement contains a function call to print value. We step into the function and the arrow will move to the top of the body of print value, line 4. Okay. Choose step into again to execute the opening brace of function print value, which will advance the arrow to line 5. Choose step into again, which will execute the statement character output value and move the arrow to line 6. Warning. The version of operator extraction used for output is implemented as a function. As a result, your IDE may step into the implementation of the operator function instead. If this happens, you'll see your IDE open a new code file and the arrow marker will move to the top of a function named operator. This is part of the standard library. Close the code file that just opened and then find and execute step out debug command. Instructions are below under the step out section if you need help. Okay, step out of it. I assume that means like go backwards, right? Now, because character output value has executed, we should see the value 5 appear in the console window. Tip. In a prior lesson, we mentioned that character output is buffered, which means there may be a delay between when you ask character output to print a value and when it actually does. Because of this, you may not see the value 5 appear at this point. To ensure that all output from character output is output immediately, you can temporarily add the following statement to the top of your main function. Enable automatic flushing for character output for debugging. Interesting. For performance reasons, this statement should be removed or commented out after debugging. You don't want to continually add, remove, comment, uncomment the above. You can wrap the statement in a conditional compilation preprocessor directive covered in lesson 2.10. Introduction to the preprocessor. If debugged, okay. You'll need to make sure the debug preprocessor macro is defined either somewhere above the statement or as part of your compiler settings. Choose step into again to execute the closing brace of function print value. At this point, print value has finished executing and control is returned to main. You will note that the arrow is again pointing to print value. Okay. While you might think that the debugger intends to call print value again, in actuality, the debugger is just letting you know that it returned from the function call. Choose step into 3 more times. At this point, we have executed all the lines in our program, so we are done. Some debuggers will terminate the debugging session automatically at this point. Others may not. If your debugger does not, you may need to find a stop debugging command in your menus in Visual Studio. This is under debug, stop debugging. Note that stop debugging can be used at any point in the debugging process to end the debugging session. Congratulations, you've now stepped through a program and watched every line execute. Tip: in future lessons, we'll explore other debugger commands, some of which may not be available unless the debugger is already running. If the desired debugging command is not available, step into your code or start the debugger and try again. Step into your code to start the debugger and try again. Step over. Okay. Like step into, the step over command executes the next statement in the normal execution path of the program. However, whereas step into will enter function calls and execute them line by line, step over will execute an entire function without stopping and return control to you after the function's been executed. Interesting. Step over command, F10. Let's take a look at an example where we step over the function call to print value. First, we use step into on your program until the execution marker is on line 10. Now choose step over. The debugger will execute the function, which prints the value 5 in the console output window, and then return control to you on the next statement, line 12. The step over command provides a convenient way to skip functions when you are sure they already work or are not interested in debugging them right now. Step out. Unlike the other two stepping commands, step out does not just execute the next line of code. Instead, it executes all remaining code in the function currently being executed, then returns control to you when the function has returned. Step out is Shift F11. Okay. Let's take a look at an example of this using the same program as above. Step into the program until you're inside the function print value with the execution marker on line 4. Then choose step out. You will notice the value 5 appears in the output window and the debugger returns control to you after the function has terminated on line 10. This command is most useful when you've accidentally stepped into a function that you don't want to debug. A step too far. When stepping through a program, you can normally only step forward. It's very easy to accidentally step past, overstep the place you wanted to examine. If you step past your intended destination, the usual thing to do is stop debugging and restart debugging again, being a little more careful not to pass your target this time. Step back. Some debuggers, such as Visual Studio Enterprise Edition, and RR, I don't know what that is, have introduced a stepping capability, generally referred to as step back or reverse debugging. The goal of a step back is to rewind the last step, so you can return the program to a prior state. This could be useful if you overstep or if you want to re-examine a statement that just executed. Implementing step back requires a great deal of sophistication on the part of the debugger, because it has to keep track of a separate program state for each step. Because of the complexity, this capability isn't standardized yet and varies by debugger. As of the time of writing, January 2019, neither Visual Studio Community Edition nor the latest version of CodeBlocks support this capability. Hopefully at some point in the future, it will trickle down into these products and will be available for wider use. What is it? Step back, right? Yeah, no, into and over. Okay. Out. Nope. Yeah. Well. Beggars can't be choosers, I guess. I'm starting to lose steam, but I'm trying to... How much is left of section 3? Oh. We might be able to finish this, maybe? That'd be nice. I think we can. Let's do it. I think let's do it. Right? Hang on. Well, how long is this one? Alright, well, I don't need a full break, but I do think I need to go to Memo for a minute. Wait, what? Memo? Are we here? We're here. Okay. Also need to mute the mic. I need to use my inhaler and things. Just need to refresh. I'll get this. I think we're good. All right. Mel, I think we're all set. Okay. Ooh, we got it. 3.7. I really think if we can finish out this section, I'll feel very accomplished. Might be a lot. Like, I'm already getting a little tired, but we might be able to do it. It's worth a shot. I might read a little faster. Like, we'll go on to 1.5 speed. Yeah, we're gonna hydrate. Okay. Excuse me. .7. Using an integrated debugger, running and breakpoints. While stepping, covered in lesson 3.6, using an integrated debugger, stepping, let me read faster. While stepping is useful for examining each individual line of your code in isolation. In a large program, it can take a long time to step through your code to even get to the point where you want to examine in more detail. Fortunately, modern debuggers provide more tools to help us efficiently debug our programs. In this lesson, we'll look at some of the debugger features that let us more quickly navigate our code. Run to cursor. The first useful command is commonly called run to cursor. This run to cursor command executes the program until execution reaches the statement selected by your cursor. Then it returns control to you so you can debug starting at that point. This makes for an efficient way to start debugging at a particular point in your code, or if already debugging, to move straight to some place you want to examine further. Excuse me. For Visual Studio users, in Visual Studio, the run to cursor command can be accessed by right-clicking a statement in your code and choosing Run to Cursor from the context menu, or by pressing Ctrl F10 keyboard combo. Interesting, okay. Let's try using the same program we've been using. Simply right-click anywhere on line 5, then choose Run to Cursor. You will notice the program starts running and the execution marker moves to the line you just selected. Your program has executed up to this point and is now waiting for your further debugging commands. From here, you can step through your program, run to cursor to a different location, etc. If you run to cursor to a location that doesn't execute, run to cursor will simply run your program until termination. Okay. Continue. Once you're in the middle of a debugging session, you may want to just run the program from that point forward. The easiest way to do this is to use the continue command. The continue debug command simply continues running the program as per normal, either until the program terminates or until something triggers control to return back to you again, such as a breakpoint, which we'll cover later in this lesson. For Visual Studio users, in Visual Studio, the continue command can be accessed while already debugging a program by a debug menu, continue, or by pressing the F5 shortcut key. Okay. F5. Oh, Control F5 is build. All right. Let's test out the continue command. If your execution marker isn't already on line 5, run to cursor to line 5, then choose continue from this point. Your program will finish executing and then terminate. Start. The continue command has a twin brother named start. The start command performs the same action as continue, just starting from the beginning of the program. It can only be invoked when not already in a debug session. Interesting. For Visual Studio users, in Visual Studio, the start command can be accessed while not debugging a program via the debug menu, start debugging, or by pressing the F5 shortcut. Okay. If you use the start command on the above sample program, it will run all the way through without interruption, except on Visual Studio Code, because we set stop at entry true in the prior lesson. That's interesting. While this may seem unremarkable, that's only because we haven't told the debugger to interrupt the program. We'll put this command to better use in the next section. Okay. Breakpoints. The last topic we're going to talk about in this section is breakpoints. Breakpoint is a special marker that tells the debugger to stop execution of the program at the breakpoint when running in debug mode. For Visual Studio users. In Visual Studio, you can set or remove a breakpoint by a debug menu, toggle breakpoint, or by right-clicking on a statement and choosing toggle breakpoint from the context menu, or by pressing the F9 shortcut key, or by clicking to the left of the line number in the light gray area. When you set a breakpoint, you will see a new type of icon appear. Visual Studio uses a red circle. CodeBlocks uses a red octagon, like a stop sign. Okay. Go ahead and set a breakpoint on the line 5, as shown in the image above. Now, choose the start command to have the debugger run your code. And let's see the breakpoint in action. You will notice that instead of running all the way to the end of the program, the debugger stops at the breakpoint, with the execution marker sitting on top of the breakpoint icon. It's just as if you'd run to cursor to this point. Breakpoints have a couple of advantages over run to cursor. First, a breakpoint will cause the debugger to return control to you every time they are encountered, unlike run to cursor, which only runs to the cursor once each time it's invoked. Second, you can set a breakpoint and it will persist until you remove it, whereas with run to cursor, you have to locate the spot you want to run to each time you invoke the command. Note that breakpoints placed on lines that are not in the path of execution will not cause the debugger to halt execution of the code. Let's take a look at a slightly modified program that better illustrates the difference between breakpoints and run to cursor. Okay. First, start a new debugging session and then do a run to cursor on line 5. Now choose continue. The program will continue to the end. It won't stop on line 5 again, even though line 5 is executed twice more. Interesting. Next, place a breakpoint on line 5, then choose start. The program will stop on line 5. You now choose continue. The program will stop on line 5 a second time. Choose continue again, and it will stop a third time. One more continue and the program will terminate. You can see that the breakpoint caused the program to stop as many times as that line was executed. Set next statement. There's one more debugging command that's used fairly uncommonly, but it is still at least worth knowing about, even if you won't use it very often. The next set statement command allows us to change the point of execution to some other statement, sometimes informally called jumping. This can be used to jump the point of execution forwards and skip some code that would otherwise execute, or backwards and have something that already executed run again. Okay. For Visual Studio, in Visual Studio you can jump the point of execution by right-clicking on the statement and choosing Set Next Statement from the context menu, or by pressing the Ctrl-Shift-F10 shortcut combination. This option is contextual and only occurs while already debugging a program. Let's see jumping forwards in action. First, run to cursor on line 11. At this point, you should see the value of 5 in the console output window. Interesting. Now right-click on line 12 and choose Set Next Statement. This causes line 11 to be skipped and not execute. Then choose Continue to finish executing your program. The output of your program should look like this: 5 and 7. We can see that print value was skipped. This functionality can be useful in several contexts. In our exploration of basic debugging techniques, we discuss commenting out a function as a way to determine whether that function had a role in causing an issue. This requires modifying our code and remembering to uncomment the function later. In the debugger, there's no direct way to skip a function. So if you decide you want to do this, using set next statement to jump over a function call is the easiest way to do so. Jumping backwards can also be useful if we want to watch a function that just executed run again, so we can see what it's doing. With the same code above, run to cursor to line 12 and then set next statement on line 11 and continue. The program's output should be 5667. Warning: the set next statement command will change the point of execution, but will not otherwise change the program state. Your variables will retain whatever values they had before the jump. As a result, jumping may cause your program to produce different values, results, or behaviors than it would otherwise. Using this capability judiciously, especially jumping backwards. Use this capability judiciously. Hello? Hello? Silent Cybermonks. Welcome. Warning. You should not use set next statement to change the point of execution to a different function. This may result in undefined behavior and likely a crash. Woo. How are you? How are you feeling? We're losing steam, but we're trying to finish this out. Step back versus jumping backwards via set next statement. Step back rewinds the state of everything, as if you'd never gone past that point in the first place. Any changes to variable values or other program state is undone. This is essentially an undo command for stepping. Set next statement, when used to jump backwards, only changes the point of execution. Any changes to variable values or other program state are not undone. Conclusion. Oh my gosh, we did. You now learn the major ways that you can use an integrated debugger to watch and control how your program executes. While these commands can be useful for diagnosing code flow issues, like to determine if certain functions are or aren't being called, they are only a portion of the benefit that the integrated debugger brings to the table. In the next lesson, we'll start exploring additional ways to examine your program state, for which you'll need these commands as a prerequisite. Let's go. 3.8. Let's do it. Using an integrated debugger, watching variables. In the previous lessons, 3.6 and 3.7, you learned how to use the debugger to watch the path of execution through your program. However, stepping through a program is only half of what makes the debugger useful. The debugger also lets you examine the value of variables as you step through your code, all without having to modify your code. As per previous lessons, our examples here will use Visual Studio. If you're using a different IDE or debugger, the commands may have slightly different names or be located in different locations. Warning: in case you are returning, make sure your project is compiled using a debug build configuration. Yes, in case we're returning. Like, we've been going though. We've been binge watching this website. Like what? For more information, if you're compiling your project using a release configuration instead, the functionality of the debugger may not work correctly. Watching variables. Watching a variable is the process of inspecting the value of a variable while the program is executing in debug mode. Most debuggers provide several ways to do this. Let's take a look at a sample program. Output X. Interesting. Pretty straightforward sample program. It prints the numbers 1, 3, and 6. Okay, 1 plus 2, 1 plus 3. Oh wait, huh? Oh. Then 3 plus 3 is 6. First, run to cursor on line 6. Okay. At this point, the variable x has already been created and initialized with the value 1. So when we examine the value of x, we should expect to see the value 1. I'm confused that these are all x's. It shouldn't be, right? In main, there needs to be just one x defined. At this point, the variable x has already been created and initialized with the value 1, so when we examine the value of x, we should expect to see the value 1. The easiest way to examine the value of a simple variable like x is to hover your mouse over the variable x. Some modern debuggers support this method of inspecting simple variables, and it is the most straightforward way to do so. Let's skip code block. Hover your mouse over variable x on line 6, and you should see something like this. Okay, we're getting a 1. X is 1. Note that you can hover over any variable x, not just the one on the current line. For example, if we hover over the x on line 12, we'll see the same value. If you're using Visual Studio, you can also use Quick Watch. Highlight the variable named x with your mouse and then choose Quick Watch from the right-click menu. Interesting. Shift F9. This will pull up a sub-window containing the current value of the variable. Okay. Go ahead and close Quick Watch if you opened it. Now let's watch this variable change as we step through the program. Either choose Step Over Twice or Run to Cursor to line 9. The variable x should now have value 3. Inspect it and make sure that it does. I see, x is getting replaced. We want to keep it as x, because x is 1. And then now 1 plus 2 makes x 3. And then 3 plus 3, you know, like, it needs to be replaced. Okay. Gotcha. The watch window. Using the mouse hover or quick watch methods to inspect variables is fine if you want to know the value of a variable at a particular point in time. It's not particularly well suited to watching the value of a variable change as you run the code because you continually have to reselect the variable. In order to address this issue, all modern integrated debuggers provide another feature called a watch window. The watch window is a window where you can add variables you would like to continually inspect, and these variables will be updated as you step through your program. The watch window may already be on your screen when you enter debug mode, but if it is not, you can bring it up through your IDE's window commands. These are typically found in a View or Debug menu. For Visual Studio, watch window can be found at Debug menu, Windows, Watch 1. Do note that you have to be in debug mode for this option to be enabled, so step into your program first. You should now see something like this. Okay, we're watching. The Watches window may or may not contain anything in it already. There are typically two different ways to add variables to the watch window. 1, pull up the watch window and type in the name of the variable you would like to watch in the leftmost column of the watch window. 2, in the code window, right-click on the variable you'd like to watch and choose Add Watch, Visual Studio. If you're not already in a debugging session with the execution marker on line 9 of your program, start a new debugging session and run to cursor to line 9. Now go ahead and add the variable x to your watch list. You should now see this. Okay. Now step over twice, or run to cursor to line 12, and you should see the value of x change from 3 to 6. Variables that go out of scope, like a local variable inside a function that has already returned a caller, will stay in your watch window, but will generally either be marked as not available or may show the last known value but grayed out. If the variable returns to scope, the function is called again, its value will begin showing again. Therefore, it's fine to leave variables in the watch window even if they're out of scope. Using watches is the best way to watch the value of a variable change over time as you step through your program. Setting a breakpoint on watched variables. Some debuggers will allow you to set a breakpoint on watched variables rather than a line. This will cause the program to stop execution whenever the value of that variable changes. For example, setting such a breakpoint on variable x in the above program will cause the debugger to stop after executing lines 8 and 11, which is where the value of x is changed. For Visual Studio users. In Visual Studio, make sure your variable is being watched. Next, step into your program and go to the Watch window. Right-click on the variable and select Break when value changes. You need to re-enable Break when value changes each time you start a debugging session. The Watch window can evaluate expressions too. Hang on, I gotta straighten up. Ugh. Okay, here we are. The Watch window will also allow you to evaluate simple expressions. If you haven't already, run to cursor on line 12. Then try entering x plus 2 into the Watch window and see what happens. Should evaluate to 8. You can also highlight an expression in your code and then inspect the value of that expression via hover or by adding it to the Watch window via the right-click context menu. Warning: identifiers in watched expressions will evaluate to their current values. If you want to know what value an expression in your code is actually evaluating to, run to cursor to it first so that all identifiers have the correct values. Local watches. Because inspecting the value of local variables inside a function is common while debugging, many debuggers will offer some way to quickly watch the value of all local variables in the scope. I like that. In Visual Studio, you can see the value of all local variables in the Locals window, which can be found at Debug menu, Local Windows, Locals. Note that you have to be in a debug session to activate this window. If you're looking just to watch the value of a local variable, check the Locals window first. It should already be there. Okay, how much more? I need to check again. 3.9, which I feel like that's a lot. Yeah. 1, 2, 3. We can do it. Using an integrated debugger, the call stack. Modern debuggers contain one more debugging information window that can be very useful in debugging your program, and that is the call stack window. When your program calls a function, you already know that it bookmarks the current location, makes the function call, and then returns. How does it know where to return to? The answer is that it keeps track in the call stack. Oh. I've heard call stack so often and it's like, I don't really know what the hell that is. The call stack is a list of all the active functions that have been called to get to the current point of execution. The call stack includes an entry for each function called, as well as which line of code will be returned to when the function returns. Whenever a new function is called, that function is added to the top of the call stack. When the current function returns to caller, it is removed from the top of the call stack, and control returns to the function just below it. The call stack window is a debugger window that shows the current call stack. If you don't see the call stack window, you will need to tell the IDE to show it. For Visual Studio users. In Visual Studio, the call stack window can be found via Debug menu, Windows, Call Stack. Okay. Let's take a look at the call stack using a sample program. A was called, B was called. Put breakpoints on lines 5 and 10 of this program and then start debugging mode. Because function A is called first, the breakpoint on line 5 will be hit first. At this point, you should see something like this. Okay. Your IDE may exhibit some differences. The format of your function names and line numbers may be different. Your line numbers may be slightly different, off by 1. Instead of external code, you may see a bunch of other crazily named functions. These differences are inconsequential. What's relevant here is the top 2 lines. From the bottom up, we can see that function main was called first, and then that function A was called next. I see. $17. Okay. I see. Main and then A. The line 5 next to function A shows us where the current point of execution is. Okay. Which matches the execution marker in the code window. The line 17 on the second line indicates the line that will be returned to when the controller returns to function main. Okay. So it's like, come back here. Tip. The line numbers after the function names show the next line to be executed in each function. Since the top entry on the call stack represents the currently executing function, the line number here shows the next line that will execute when the execution resumes. The remaining entries in the call stack represent functions that will be returned to at some point. So the line number for these represent the next statement that will execute after the function is returned to. Now choose the continue debug command to advance execution to the next breakpoint, which will be on line 10. The call stack should update to reflect the new situation. Okay, line 10, line 19. It'll return from here, from void B. It'll return down to here. You'll notice that function B is now the top line of the call stack, reflecting the fact that function B is the function that is actively being executed. Note that function A is no longer represented on the call stack. This is because function A was removed from the call stack when it returned. Choosing the continue debug command one more time and we'll hit the breakpoint on line 5 again, because function B calls function A. The call stack will look like this. You'll have all 3. There are now 3 functions on the call stack. From the top, from bottom to top. Hello. C142, thank you. From bottom to top, main, which called function B, which called function A. The call stack is useful in conjunction with breakpoints when your breakpoint is hit and you want to know what functions were called to get to that specific point in the code. Oh my god, we're going. Oh my god. Conclusion. Congratulations, you now know the basics of using an integrated debugger. Using stepping, breakpoints, watches, and the call stack window, you now have the fundamentals to be able to debug almost any problem. Like many things, becoming good at using a debugger takes some practice and some trial and error. But again, we'll reiterate the point that the time devoted to learning how to use an integrated debugger effectively will be repaid many times over in this time saved debugging your programs. We love that. All right, how long is this one? We can do it, we can do it, we can do it. Let's do it. And the next one, we get to see how much we've retained. 3.10. Finding issues before they become problems. Ooh. When you make a semantic error, that error may or may not be immediately noticeable when you run your program. An issue may lurk undetected in your code for a long time before newly
Google
introduced
this.
code or changed circumstances cause it to manifest as a program malfunction. The longer an error sits in the code base before it is found, the more likely it is to be hard to find, and something that may have been easy to fix originally turns into a debugging adventure that eats up time and energy. So what can we do about that? Don't make errors. Don't mess up. Well, the best thing is to not make errors in the first place. Here's a list of things that can help avoid making errors. Follow best practices. That's why we're reading this. That's why we're doing it. Don't program when tired or frustrated. Okay. Take a break and come back later. Understand where the common pitfalls are in a language. All those things we warn you not to do. Don't let your functions get too long. Prefer using the standard library to writing your own code when possible. Okay. Comment your code liberally. Start with simple solutions, then layer in complexity incrementally. Avoid clever, non-obvious solutions. Optimize for readability and maintainability, not performance. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Okay. She's all licky right now. Refactoring your code. Ooh. As you add new capabilities to your programs, behavioral changes, you will find that some of your functions grow in length. As functions get longer, they get both more complex and harder to understand. One way to address this is to break a single long function into multiple shorter functions. This process of making structural changes to your code without changing its behavior is called refactoring. The goal of refactoring is to make your program less complex by increasing its organization and modularity. So, how long is too long for a function? A function that takes up one vertical screen worth of code is generally regarded as too long. If you have to scroll to read the whole function, the function's comprehensibility drops significantly. Ideally, a function should be less than 10 lines. Functions that are less than 5 lines are even better. Remember that the goal here is to maximize comprehension and maintainability, not to minimize function length. Abandoning best practices or using obscure coding techniques to save a line or two doesn't do your code any favors. Okay. Key insight. When making changes to your code, make behavioral changes or structural changes, and then retest for correctness. Making behavioral and structure changes at the same time tends to lead to more errors, as well as errors that are harder to find. An introduction to defensive programming. Errors can be not only of your own making, like incorrect logic, but also occur when your users use the application in a way you did not anticipate. For example, defensive programming. For example, if you ask the user to enter an integer and they enter a letter instead, got my G earlier, how does your program behave in such a case? Unless you anticipated this and added some error handling for this case, probably not very well. Defensive programming is a practice whereby the programmer tries to anticipate all of the ways the software could be misused, either by end users or by other developers, including the programmer themselves, using the code. These misuses can often be detected and then mitigated by asking a user who entered bad input to try again. We'll explore topics related to error handling in future lessons. Finding errors fast. Since not making errors is difficult in large programs, the next best thing is to catch errors you do make quickly. The best way to do this is to program a little bit at a time, and then test your code and make sure it works. However, there are a few other techniques we can also use. An introduction to testing functions. One common way to help uncover issues with your program is to write testing functions to exercise the code you've written. Use a primitive attempt for more illustrative purposes than anything.
This function should print. Okay. Test add. I see. It's like you take a value and you just make sure it's the correct value because it's done all of the what? Right? The test add function tests the add function by calling it with different values. If all the values match our expectations, then we can be reasonably confident the function works. Even better, we can keep this function around and run it anytime we change function add to ensure we haven't accidentally broken it. This is a primitive form of unit testing, which is a software testing method by which small units of source code are tested to determine whether they are correct. As with logging frameworks, there are many third-party unit testing frameworks that can be used. It's also possible to write your own, though we'll need more language features at our disposal to do the topic justice. We'll come back to some of this in a future lesson. An introduction to constraints. Constraints-based techniques involve the addition of some extra code that can be compiled out in a non-debug build if desired, to check that some set of assumptions or expectations are not violated. For example, if we were writing a function to calculate the factorial of a number, which expects a non-negative argument, the function could check to make sure the caller passed in a non-negative number before proceeding. If the caller passes in a negative number, then the function could immediately error out rather than producing some indeterminate result. Indeterminate result, helping ensure the problem is caught immediately. One common method of doing this is via assert and static assert, which we cover in lesson 9.9, assert and static assert. Shotgunning for general issues. Programmers tend to make certain kinds of common mistakes, and some of those mistakes can be discovered by programs trained to look for them. These programs, generally known as static analysis tools, sometimes informally called linters, are programs that analyze your source code to identify specific semantic issues. In this context, static means that these tools analyze the source code without executing it. The issues found by static analysis tools may or may not be the cause of any particular problem you are having, but may help point out fragile areas of code or issues that can be problematic in certain circumstances. You already have one static analysis tool at your disposal, your compiler. In addition to ensuring your program is syntactically correct, most modern C++ compilers will do some light static analysis to identify some common problems. For example, many compilers will warn you if you try to use a variable that has not been initialized. If you haven't already, try turning up your compiler warning error levels can help surface these. We did do that, yes. 0.11. Many static analysis tools exist, some of which can identify over 300 types of programming errors. On our small academic programs, use of a static analysis tool is optional, but using one may help you find areas where your code is non-compliant with best practices. On large platforms, use of a static analysis tool is highly recommended as it can surface tens or hundreds of potential issues. Oof. Best practice. Use a static analysis tool on your programs to help find areas where your code is non-compliant with best practices. For Visual Studio users, Visual Studio 19 onward comes with a built-in static analysis tool. You can access it via build, run, code analysis on solution. Alt F11. Tip. Some commonly recommended static analysis tools include, for free, Clang Tidy, CPP Lint, CPP Check, already integrated into CodeBlocks, and Sonar Lint. Most of these have extensions that allow them to integrate into your IDE. For example, Clang Power Tools extension. Paid may be free for open source projects. Coverity, Sonar Cube. We did it. Oh my god. We made it. So review. And then quiz. I'm like, do we skip the quiz maybe? Oh, just real quick. It's hard to find good examples of simple programs that have non-obvious issues to debug. Given the limited material covered so far, any readers have any suggestions? I really liked the, what was it? Oh, it was, like the forward declaration said that there'd be 2 ints. And then when the function was actually called, there was 3. Like stuff like that. I had like not noticed it till like the last second. I was like, wait, that's wrong. It's like not crazy obvious. You're just like, yeah, I called it. I may want to skip the quizzes. We can maybe start with the quizzes next time. I'm so tired. Divide 2 numbers. Extra credit. Uh-oh, now I'm like, oh, let's get this extra credit. Following program is supposed to add 2 numbers, but it doesn't work correctly. Use the integrated debugger to step through this program. For inputs, enter 8 and 4 based on the information you learn. Fix the following program. Whew. Maybe we will. Maybe we will. Let's read this. 3.x. Chapter 3 Summary and Quiz. Chapter Review. A syntax error is an error that occurs when you write a statement that is not valid according to the grammar of the C++ language. The compiler will catch these. I'll catch them. I'm like, I don't want to do the quizzes. Okay. A semantic error occurs when a statement is syntactically valid but does not do what the programmer intended. The process of finding and removing errors from a program is called debugging. We can use a 5-step process to approach debugging. 1. Find the root cause. 2. Understand the problem. 3. Determine a fix. 4. Repair the issue. 5. Retest. Finding an error is usually the hardest part of debugging. Static analysis tools are tools that analyze your code and look for semantic issues that may indicate problems with your code. Being able to reliably reproduce an issue is the first and most important step in debugging. There are a number of tactics we can use to help. Just realized. I am going to leave the quizzes for next time so that, because we read this whole chapter in one go, and normally chapters have kind of been split between streams, so I feel like we should start at the quizzes next time, you know? I'll probably label it chapter 4, but we'll just do these real quick because it looks like we're just jumping through the debugger. It'll be quick, but I want to make sure that we've retained this, so we should use the quizzes to be sure that it was retained, you know? All right, sorry. Finding an error is usually the hardest part of debugging. Static analysis tools are tools that analyze your code and look for semantic issues that may indicate problems with your code. Being able to reliably reproduce an issue is the first and most important step in debugging. There are a number of tactics we can use to help find issues. Commenting out code, using output statements to validate your code flow, printing values. When using print statements to debug, use standard C error instead of character output, but even better, avoid debugging via print statements. A log file is a file that records events that occur in a program. The process of writing information to a log file is called logging. The process of restructuring your code without changing how it behaves is called refactoring. This is typically done to make your program more organized, modular, or performant. Unit testing is a software testing method in which small units of code are tested to determine whether they are correct. Defensive programming is a technique whereby the programmer tries to anticipate all the ways the software could be misused. These misuses can often be detected and mitigated. All of the information tracked in a program, variable values, and functions have been called, current point of execution, is part of the program state. A debugger is a tool that allows the programmer to control how a program executes, examine the program state while the program is running. The integrated debugger is a debugger that integrates into the code editor. Stepping is a name for a set of related debugging features that allows you to step through your code statement by statement. Step into executes the next statement in the normal execution path of the program, then pauses execution. If the statement contains a function call, step into causes the program to jump to the top of the function being called. Step over executes the next statement in the normal execution path of the program, and then pauses execution. If the statement contains a function call, step over executes the function and returns control to you after the function has been executed. Step out executes all remaining code in the function currently being executed and then returns control to you when the function has returned. Run to cursor executes the program until execution reaches the statement selected by your mouse cursor. Continue runs the program until the program terminates or a breakpoint is hit. Start is the same as continue, just from the beginning of the program. A breakpoint is a special marker that tells the debugger to stop execution of the program when the breakpoint is reached. The set next statement command allows us to change the point of execution to some other statement, sometimes informally called jumping. This can be used to jump the point of execution forwards and skip some code that would otherwise execute, or backwards and have something that already executed run again. Watching a variable allows you to inspect the value of a variable while the program is executing in debug mode. The watch window allows you to examine the value of variables or expressions. The call stack is a list of all of the active functions that have been executed to get the current point of execution. Call stack window is a debugger window that shows the call stack. Okay, I'm going to do the typing test at the very least, if I'm going to be bailing on the quiz this time, you know. It's just too much. I've been sitting too long. I also do feel like using the quiz as a refresher will be smart. Alright, let's see for anybody. I'm looking. Oh, let's restart. Can't look. And let me move. I gotta move like there we go. This freaking guy. Okay. My hand here. Okay. And void. And then let's just, since we're in a rush anyways, and I was gonna say let's just do no fixing shit and see how fast we are anyways, because we're supposed to not fix it. So son of a bitch, because then we're not getting a good idea of our accuracy. What accuracy? Shit. Oh, I'm scared. Oh my god. Oh, fuck. Oh no. Kill me. We're gonna be for sure faster than 12 this time, you know? No. No. No.
I don't know why I is really hard today. Also, why is engine so easy for me to write? I don't understand. But then sometimes it isn't. Literally. No. No. Q. Oh, maybe we shouldn't be fixing. You know? Just keep doing this till it's 100% accuracy. Then we never have to hit the backspace, you know? Like, why is engine so easy? But then... What the hell? What the hell? Shit. Damn it. Oh, damn it. Okay. Words per minute 4. Never mind. We did terrible. No words. 83%. Alright, we did it. How y'all doing? How we doing? How we feeling? I'm not feeling that great. That was a lot, but I also am feeling good about how much we've accomplished in just a day. Alright, what we got? Who's here? Ooh, hang on. Quite a lot, actually. A lot of people are live. Ooh, give me a second. A lot of options. I need to check out this one. See how long that's been going. And then this one. Nobody look. Nobody listen. Twitch. Be quiet. Be quiet. Please. I don't want to save 15% or more on car insurance. Okay, hang on. Alright, how long's this one been going? Oh, half an hour. And this one. 7 minutes. Ooh. Hang on. One of them I know what the game is. The other one I don't know what the game is. So I need a moment. Hold up. Wait for the ad to finish. This looks interesting. Okay, I think... Alright. I know what we're doing. Took me a minute. Hold on a second. I know, yeah, we did so much. Excellent. I'm excited to get into like the double digit sections, you know? Alright. We're gonna raid Little Spectre. Airhammer raided out to them recently and they were playing Animal Crossing. And there was like no mic or anything, so it was just like chill. I had it on the TV. It was very relaxing. So yeah, let's copy the raid message, which I feel like I need to update that, but let's say hi. So I'm gonna send you guys out. Thank you guys for being here. I'm hoping I can maybe stream Tuesday, maybe not. We'll see. Maybe tomorrow when I feel like it. But I definitely want to keep going. So enjoy
Lil Spectre, playing Stardew Valley. I don't know if I said that, but let's relax after all of this working. Okay. See you guys next time. Bye.